Hi, welcome to me313 Mechanical Engineering Thermodynamics. Topic of this lecture is air-water mixtures, and the sections in the textbook are 14.1 to 14.4. So here are the learning outcomes. At the end of this, you'll understand qualitatively why air often has some water vapor in it. You will know how to quantify the energy content of that moist air, and we'll be using enthalpy primarily for that. You'll be able to define relative and absolute humidity. Absolute humidity is also known as specific humidity. And you will understand what is the dry and wet bulb temperature and the dew point temperature. So first, I want to talk qualitatively about air-water mixtures and get an understanding of why is there some water vapor in air. So first, imagine like I've got this glass of water over here, and imagine it's sealed for now up at the top. And there's just air on the top and just pure water on the bottom. If we just let it sit there, what we'd find is some water molecules would leave the liquid and would go into the air phase, and we would end up with a mixture up there. We would have an air-water mixture. And this is going to go ahead and continue for quite some time, but it won't happen infinitely long. At some point it'll stop and there'll be a certain number of water molecules in the air, and that will happen at equilibrium. And you might say, well, why does that spontaneously happen? Well, if you remember, when we have two things that are pure, they tend to want to mix. And the reason they want to mix is because there's going to be an increase in the entropy. So the change in the entropy, if we just maybe to take that first water molecule, well, we would have Cp, we have ln of T2 over T1. And if it's just one water molecule, there wouldn't be much change. That's about 0. So you might remember this from the last chapter. And then we have minus R, and then it would be the natural log of the pressures. And so we can express those partial pressures in terms of the mole fractions, and so it was this minus R ln of Yi, where Yi is the mole fraction of water vapor in air up here. And what we realize is that if this initially started out as pure air and then I put water molecules in it, the entropy goes up. And so it turns out things that spontaneously increase the entropy are going to happen, or I should say processes that increase the entropy will happen spontaneously. And the reason that it happens, and we'll look at more at this when we get into chapter 16, is something called the Gibbs free energy, which we've already been introduced to in chapter 12, which was defined as H minus Ts. And so what we realize is that when the entropy goes up, the Gibbs energy goes down. And it turns out nature wants to minimize the Gibbs free energy. Again, we'll look at more of this in chapter 16, but qualitatively, that is what is going on. And so if we were to talk about what the Gibbs free energy is of the air-water mixture, actually we should use something called the chemical potential, because it's a mixture. And if you want to learn more about the chemical potential, you should read the little special section at the end of chapter 13. But the chemical potential of this mixture right over here is going to, we'll call it mu of the mixture. There's also going to be a chemical potential of the water down here. And so the chemical potential has two components. It's going to be that of the pure material, and then there's going to be an additional component that I add to it, which is equal to R T and the natural log of the mole fraction that's in it. And what I realize is this is going to be a number between 0 and 1, which means that this chemical potential is going to decrease. It's very similar to the Gibbs free energy decreasing. And so if I was to go ahead and plot the chemical potential as a function of the mole fraction, starting off at 0, meaning it's pure air, and then I start adding water to it, this is going to go ahead and decrease, and at some point it's going to end up being at some sort of minimum value. And in fact, at that point, the Gibbs free energy of the mixture up here will be the same as pure water. And that's the point of 100% saturation, and that's when this process will end. So qualitatively, that's what's going on. We're trying to minimize this Gibbs free energy, or effectively set the chemical potential of the mixture and the pure water equal to each other. Now, one last thing you might notice is I'm not talking about air being dissolved in water, and it turns out there tends to be very little air dissolved in water. And so if we just assume that the water is pure water, that's actually a pretty good assumption. All right, so let's talk a little bit about quantifying the energy content of air-water mixture. So first, let's just consider I have pure air over here, and air at atmospheric pressures and temperatures is what we're interested here in this chapter primarily, is around 1 atmosphere and room temperature, which means it acts as an ideal gas. And so if it acts as an ideal gas, the enthalpy we know is just a function of temperature, and in fact we can quantify it as the heat capacity times temperature. And heat capacity in English units is about on the order of about 1.01 kilojoules per kilogram. And so then I could go ahead and multiply that by the temperature. And that will be the enthalpy. And I'll call it HA because it's the enthalpy of the air. Well, now I'm going to go ahead and add some water. So maybe I had some liquid water on the bottom, like my glass before, glass of water. And now I've got these blue molecules, which are water molecules that have gone in. And now I want to quantify what's the energy content of this. Now this is, if you remember from mixtures, if this is also an ideal gas, and because the water tends to be pretty small, it's maybe 0.5% or 1% of all the molecules, partial pressure is very low, it's also going to act as an ideal. So I've got an ideal gas mixture now. And so that's pretty simple. If I want to quantify the enthalpy, I'm just going to add the enthalpy of the air plus the enthalpy of the water together. So now I need to go ahead and quantify what's the enthalpy of the water. How much did it add to this mixture? Well, what I have liquid that then went into the vapor phase. My enthalpy is going to end up being, this is the enthalpy of the water, is going to be the enthalpy of vaporization, which is HFG, and then maybe I'm going to go ahead and raise this up to some temperature. So maybe we'll say this is at, say, 25 degrees Celsius. I'll take the HFG value at 0 degrees Celsius, and then I'll add a CPT term to it right there. Now this is the CP of water vapor, and so these values here is about 2501, this is in SI units, plus 1.82 times the temperature. This is the CP of the water vapor. And now I'm going to add these two together. So my enthalpy, the enthalpy of the air, plus the enthalpy of the water. And so maybe let's say that I've got 1 in 100. So I have a 1% mixture of water vapor and air. I would then go ahead and say, well, the enthalpy of the air is, I'm going to use my basis point of 0 degrees Celsius so that I keep both of these the same. I'm going to have 1.01 times 25, which is the enthalpy of the air, and then I've got about 1% of it is water vapor, and I have 2501 plus 1.82 times T, and that is about 50 kilojoules per, and then the unit here, since I've got both water and air, is we tend to talk about kilojoules per kilogram of dry air. So I'm going to keep the amount of red molecules constant, and we'll realize that that's actually a pretty convenient way to go ahead and do that. I want to talk about a couple more terms here, which is absolute and relative humidity. And so first I'll talk about the absolute humidity. This is also called the specific humidity. And what that is the amount of water vapor in air. So it's the amount of blue dots per amount of red dots. And so it's given the symbol omega, and it's simply the mass of the water vapor over the mass of the air. And it tends to be pretty small. It might be, as I said, maybe 0.5% or 1%. So this is a mass per mass and is often reported as maybe grams per kilogram of dry air. There's sometimes kilograms per kilogram, at which point it'll be a fairly small number. But it's relatively a number on the order of 1%. So that right there is what the absolute or specific humidity is. And another term that we often talk about, though, is the relative humidity. So first of all, let's imagine now I'm going to add more water molecules. So I've got more blue dots in here. Omega is going to increase because I'm adding more water vapor per the amount of air. Okay? But that's going to stop at some point when I've reached the holding capacity. Right? So we can talk about what the holding capacity is. And we saw this before, actually, in ES346, that when the partial pressure of the water vapor is equal to the saturation pressure at that temperature, that is going to be 100% saturation. And that's what we call the relative humidity, and that symbol of that is 100%. So if it's not completely saturated, phi, right over here, is going to be something less than 100%. And so what we realize is that this value of the relative humidity is going to be the mass of the water vapor relative, I'll call it maybe the mass, the maximum amount that it can hold, which is mv over m at saturation. And the way that the book writes this is mv over m sub g. All right? So it's the maximum amount that it can hold, which is the mass that we would have at saturation, and the book uses m sub g. And since we can use the ideal gas law to describe this, we have PV equals mRT at the same temperature and the same volume. I can go ahead and replace this with pressures. And so what I find is the relative humidity is the partial pressure of the water vapor over that saturation pressure. And so since the saturation pressure is a function of temperature, we realize that the relative humidity is also a function of temperature. And that will become important when we start talking about some of these other temperatures here in just a moment. This value of the relative humidity is always between 0 and 1, or 0 and often written as 100%. We'll express it as a percentage value. I want to talk about the dew point temperature now. And so what we'll see in this slide and the next one is there's a couple other ways to quantify the amount of water vapor that's in air. We can use the relative humidity or the absolute humidity. We can also do something called the dew point temperature. So let's imagine this experiment. I've got a water vapor mixture, and I'm going to go ahead and slowly cool it down. Right? So as this cools down, the absolute humidity or specific humidity is going to remain constant because the mass of water per air is not changing. But what I realize is that the relative humidity is going to decrease. And the reason that the relative humidity is decreasing is that Psat is going down as well. And so at some point I'm going to end up with my water vapor is equal to that saturation at that temperature. At that point, phi would be equal to 1, and we call that the dew point. Because water, now liquid water, would begin to condense out. And you've probably seen this before. This is like dew that you see in the morning. On summer nights, as the evening progresses along, it gets colder, and at some point this condition holds and water just drops out. You also tend to see condensation on windows, and the reason you see that is that if it's colder outside than inside, the air right near the window is about more or less the temperature outside, and so we get condensation on the window. So there are a couple other ways we can quantify the water content. And one way we can do that is using something called the wet bulb temperature. And so I want to go ahead and explain what the wet bulb temperature is. And so first, let's imagine this experiment here. I've got an air-water mixture that's coming in on this side. Okay, it's not completely saturated, and then it's blown over this tank of air that's really long. And so what happens is as the air moves through here, water molecules are going to go in spontaneously, as we discussed in the very first slide, until this is completely saturated. Now, if this happens while it's adiabatic, so I don't allow any energy to go in or leave the system, what ends up happening is that this air temperature is going to decrease. And so T2 is going to be less than T1 because it had to go ahead, the air had to supply the energy in order to vaporize the water or evaporate the water. The drier this is that comes in, so if this comes in very, very dry, T2 is going to be much less than T1. If it comes in near saturation, I would find that T2 is going to be close to T1 because not much water was going to be absorbed and the temperature didn't drop down too much. Right? Well, this temperature that is coming out, this T2 that is less than T1, right, is called the wet bulb temperature. And the reason it's called the wet bulb temperature is because a practical way to run this experiment instead of this big long chamber is to go ahead and take a thermometer and then put like a big cotton ball on the bottom or a wick on it. And then what happens is if you were to blow air on it, air is going to go through that wick that is wet. It's going to absorb some water. It's simulating what's occurring here. And then when it hits the bulb of the thermometer, it's going to be cold. It's going to be T2, and it's going to be the temperature recorded by a wet bulb. And the practical way to go ahead and do this, because this is a measure of how dry the air is, which is ideally we want to do, is something called the sling psychrometer, which I show here on the left. And what you do is you have two thermometers. You have one that's just sitting there, and it's recording what the actual air temperature is. And then over here we have that wick, or that sponge, that we go ahead and add water to it. And then we go ahead and just kind of spin this thing around in the air to go ahead and force air through that. This thermometer on the left-hand side is going to be somewhat less than that on the right, because the larger the difference, the drier the air is. This temperature of that bulb that is dry, is the dry bulb temperature is just the actual temperature in the room. And then this one over here is going to be recording a temperature lower, and the lower it is, the drier the air is in the room. So it's another measure of the amount of water content that I have in the room. All right, so I just kind of want to summarize some of this stuff so you understand what we were doing. We talked about a lot of qualitative things in this video. First, I want to mention the Gibbs phase rule, and you'll see this again. And we've actually seen this. This is actually where the state postulate is. And so let me just go ahead and explain what this is. The number of independent variables that describe a system is the number of components minus the number of phases plus 2. So let's think back. Before we talked about mixtures, we had the state postulate that said we need 2 independent properties to describe a system. Well, that's because we had 1 component and we had 1 phase, 1 minus 1, and plus 2. So that meant we had to have 2. So for example, we could use T and P, or T and D, or H and S, or any 2 of those. Well, now we're talking about mixtures, where now our number of components is 2, and then in the vapor phase, we've only got one phase. So we have 2 minus 1 plus 2, and so you would actually need 3 intensive variables to describe it, like pressure, temperature, and then what you would need would be the mole fraction. But what we'll see is we tend to go ahead and keep pressure constant at like atmospheric temperature. That's normally where we're interested in HVAC type things. So then we'll reduce down to 2, and the 2 that we need are, for example, temperature and then the amount of water that I have. Or think of it as the mole fraction Y sub I, or any of these various things that we looked at. So we want temperature and water content as our 2 properties to describe the system. And we can describe the water content in many different ways. We can use the absolute humidity, we can use the relative humidity. Remember, both of those are more or less direct measurements of the amount of water in the air. But we can also use the dew point temperature, because that gave us an idea of how saturated it was. If the dew point temperature is equal to the absolute temperature, we're 100% saturation. The lower the dew point is from our beginning temperature, the drier the air was. And then we also could do that wet bulb experiment, which also gives us an indication of the amount of water in the air. Right? So now, since relative humidity, the dew point temperature, and the wet bulb temperature, they're all functions of both the absolute humidity and temperature, that means I can actually use any 2 of these properties to give myself my 2 required independent variables. So I could use, for example, temperature and relative humidity, temperature and absolute humidity. I could use the dew point temperature and relative humidity. Any 2 of those is going to go ahead and completely define my system. And we'll see that more when we start using the psychrometric charts in future videos, and then also when we use EES.